Perfect. Yeah, is it on now? Is it recording? Good. So all my side comments about Thorne-Zytkow objects not recorded. Phew. Bondi-Hoyle accretion. So you have a neutron star. It's falling into this, spiraling into this star, its companion. How do you estimate how much material accretes onto it? There's a fairly simple estimate that you can do. You can compare you can look at the centrifugal force of material flowing by it. So if I have an object, material is flowing by it, it has some velocity. If it were going fast enough, it would go in an orbit, right? If it's going less than that, it's going to spiral in. Well, that's just sending the centrifugal force to the gravitational force, and I can derive the radius. If the neutron star is going through some material, I can derive the radius at which this material will fall in based on the velocity that I'm moving. So it's as simple as that. If I have a neutron star in the center of a dense medium, material is just going to flow onto it if there's no velocity. If I put in the velocity of that motion through it, I can derive that radius. That's called the Bondi-Hoyle radius, and it's g mass of the neutron, the gravitational constant times the mass of the neutron star divided by that velocity squared. So I can derive what that Bondi radius is. Now, there was Bondi, Hoyle, and Littleton were all deriving this. They realized, well, if there's some sound speed, if the matter is moving itself, it will also be unbound, even if it's not moving at all, because there's some motion. So they did a nice little, if you need to somehow implement two different terms, the simplest one is quadrature, so they did the sound speed squared plus the velocity squared. So they did some simple model like this, and you can then derive what is the Bondi radius when I have thermally heated material and I'm moving a neutron star through that medium. So we have something that gives you the Bondi radius. You can then calculate the accretion rate onto that, and I have now a Bondi radius 4 pi r squared big. I have a neutron star moving into it, and I ask what's the density and what's the velocity, and that's the capture cross section. So it doesn't look any different than any other kind of capture cross section. That tells you what's the amount of mass that I would be accreting. Then you have some coefficient up in front, which is, I've done this analytic derivation. It's very simple. Real physics makes it a little bit different. So I have some parameter that I have to move that by. But the parameter turns out to be not so bad when you do calculations. It's roughly close to 1. And we've done lots of detailed calculations of this. Here's some recent results by Mordecai McLeod. There's old results by Ruford and Arnett in 1994, where they took neutron stars, put them into media, and they let material accrete. What makes it difficult when you're doing common envelope calculations is that there's a density gradient and a velocity gradient as you're spiraling in. And so that effect lowers your efficiency at which you accrete onto this object. So the first question I have is, how fast am I accreting onto my neutron star? And I can do this just with the Bondi-Hoyle assumption. So it's really simple analytic. I'm just deriving what is, the material has some velocity. When gravitational force is pulling it faster than the centrifugal force is pushing away, it will accrete on. So you get matter accretion. The Bondi-Hoyle formula is pretty good. It's within a factor of a few of the answer, except for really steep density gradients, because then you'll get a lot of angular momentum that's causing problems. So people have done these calculations. Here's some results by McLeod where he's calculating the mass accretion rate versus this density gradient. So this epsilon rho is the density gradient. So 0 would be no density gradient at all. Then he has a huge density gradient on one side, and he's asking the question of what is the accretion rate. And you can see if you have a really big, he has two different models. The blue and the magenta are 4/3 and 5/3 gamma log gases. And he has those two different models. And then he has what he's getting for the accretion rate. And it's near 1 or 3 to 1 with no gradient. And as he goes down, it gets a higher and higher density gradient. It can drop by an order of magnitude. So that's the kind of results people are doing. They're studying this accretion rate. We know we're starting to understand what flows down onto the neutron star. So that's just what flows down onto the neutron star. That doesn't tell you can't have a Thorne-Zytkow object. That just tells you the material is going to go down into the neutron star and pile up on it. So the next question you would want to do is exactly what happens once that material piles up on the neutron star. And that's when you need to actually start studying what, when this material comes down, it releases a lot of potential energy, it heats up, it wants to radiate. That gets to our next analytic derivation, which is called the Eddington luminosity or Eddington accretion rate. What Eddington did was he said, look, if I have something that is emitting radiation, I have a force that's pulling it in, which is gravity. I have a force that's pushing out, which is if it's a free streaming solution, the radiation scatters, gives some of its momentum to the inflowing material. And that is, I'm comparing the radiation momentum or the radiative force to the gravitational force. So the radiative force is right here, this F rad. It's the luminosity divided by 4 pi r squared. That's just making it spherical, so I'm assuming a spherical approximation. Then I have sigma, which is the cross section for that radiation. So if you just assume scattering, you can, and you assume that you're mostly ionized, we know exactly what that opacity is, and that's what they typically use. They say if it's hydrogen and it's scattering, the sigma is 0.4 centimeters squared per gram. So it's a value, we know it. If you have heavier metal, if you have anything heavier than that, it's 0.2. But you have the opacity, and then c is the speed of light. So that's the radiative force. I can set that radiative force equal to the gravitational force, and I can derive the Eddington luminosity, which is if I have this luminosity, I will, that is, no material can flow back in, because that luminosity, the radiation is driving out anything that might want to fall in. So most stars, they emit at the Eddington luminosity. You can't get much higher than that, because otherwise they would be blowing off their envelopes. You can then turn that around and say, now let's assume when I accrete, that my luminosity is coming from accretion. I can derive an Eddington accretion rate. And so if I have a neutron star and I'm accreting, I can say my maximum accretion rate is the one where I get to the Eddington luminosity. So I assume all of my energy gets converted from gravitational potential energy to photons. And then I could give a limit on the accretion rate. And this is exactly what Thorne and Zytkow decided to do. They said, okay, I have this. I have the energy that's released when I collapse down. I accrete some of that material. That gives me a luminosity. And that luminosity is going to support my star. And so I'm just going to get a slowly evolving star that's accreting at this rate to power it. And that's going to be the power of my star. The problem with that is that you make some assumptions on what the radiation is doing. One is you're assuming that the radiation is not trapped in the flow. So the radiation is free streaming. You're making that assumption. So you can calculate what is the radiation, how fast is the radiation diffusing outward. And Roger Chevalier did this derivation in the early 90s, where he said, okay, well, I know what the diffusion approximate. The problem is we know for these conditions of these common envelope, the radiation is in a diffusive limit. So already you can think, maybe this nice Eddington limit is not going to work here, because we're in a very dense region where it's in the diffusion limit. But let's do the calculation anyway. I'm in the diffusion limit, so I can calculate how, the time it takes is just a random walk. So I can derive a random walk derivation for how quickly does a photon get out, and what's the photon average velocity. So you can term it in a velocity where I can talk about the velocity of the photons through diffusion. How fast are they moving outward? And I can compare that to the infall time, this free fall infall time of the material falling in. And Roger Chevalier, he did this, and he called this the trapping radius, where he said, I'm going to set, that's where it's equal. That's where the radiation is moving outward as much as the matter is flowing inward, which means the radiation is getting pulled. If the radiation is moving out slower than it's pulling inward, it's coming in the flow. So typically when we do supernova, we're releasing a lot of energy. How come we don't worry about this in our supernova core collapse? Why are the photons not supporting the star? Because the photons are trapped in the flow. They just fall in with the star. They don't move out. The trapping radius, if you plug in all those numbers, you go do your calculations, the trapping radius for photons is essentially the size of the star. Once it goes into this common envelope, the photons are trapped, which means I cannot use the Eddington luminosity to do this derivation because the photons are trapped in the flow. They are not exerting a pressure because they're not making it out. They're falling in. So the question is, what happens? What really happens with these atmospheres? So what does nature really do? Well, we do calculations of this where we model this infall, and we can model what's the profiles of the accreting material. And this is a plot of, so this gets back to my thesis. This is a plot, so 1996, it tells you how old I am. This is the entropy on the y-axis, the log radius on the x-axis, and it shows you what happens is I just let material fall onto this neutron star and pile up. And so it's piling up, and you get a thing there where you get a, if your equation stays roughly radiation dominated, which it is for this material, you get an entropy gradient where you have high entropies and it slowly decreases. And then the edge here is where that shock is. So material is piling up and making it shock, and it's piling up on this atmosphere. So we can even derive the properties of this atmosphere. And when Roger Chevalier did this, he said, okay, look at that entropy gradient. It's going to be convectively unstable, and it's going to quickly evolve to a constant entropy atmosphere. And here are the properties of the atmosphere. This is derived by Serling Colgate and Mark Arant and Willie Benz, where they had, okay, well, and it was done before. This is a simple equilibrium atmosphere. So you know what the pressure, the density, the temperature of this atmosphere is for any kind of reasonable entropy. And the entropies that you can imagine getting at best are things like below, a typical star is around 10 to 50 Boltzmann constant per nuclei, just to give you a number of what is reasonable. You can get up to 500 or even 1,000 Boltzmann constant per nuclei in these atmospheres as they crash down on, because you shock them and heat them up. So you can get some high entropies, but they're still around 1,000 Boltzmann constant per nuclei. And then you can plug that in and say, what are the temperatures and the density conditions in that atmosphere? And the question is, what does that atmosphere do? So I might be able to still make a Thorne-Zytkow object if I can have that atmosphere slowly leak out radiation and support the rest of the star. However, if you look at any reasonable value for those atmospheres, there's another piece of physics, and this is where we get back to White's mandate. Anything that's not strictly forbidden by physics. Well, if I don't put in this piece of physics, then maybe I can make a Thorne-Zytkow object. But if I put in the fact that at some point I have high temperatures, and at least through electron-positron pair annihilation, I'm going to make neutrinos, I suddenly have another place to lose my energy. So if I could sit there and just wait for the radiation to get out, I would support my atmosphere and I'd be great. But now I'm emitting neutrinos. So all my energy that I released, this nice power source, I'm throwing away because I'm emitting neutrinos. And these atmospheres are they're dense to photons, but to neutrinos, they're just leaking out. They just stream out. So I'm not saving that energy. All that energy is just going away. I lose it all through neutrino cooling. And so this is the end. The Eddington limit cannot apply, because the Eddington limit, the assumption was that all the energy got converted into photons, and all of the energy is getting instead converted into neutrinos. So that's the first part of my talk. That is why, the idea of a neutron star with an envelope on top of it, it doesn't happen. Nature forbids it. So physics forbids it. So the first example of where White's mandate was explicitly stated, because astronomers do it all the time, but this one it was explicitly stated, is an example where physics actually did forbid it. So it is not allowed. So the question is, what does happen when you take a neutron star and let it spiral in to a stellar core? And that was in the gamma ray burst community, we know this. It's actually called and it's okay. I apologize for the name. Clearly, I blame Stan, because clearly Stan was my mentor at the time, and as clever as we could come up with was Helium Merger GRB. The Helium Merger GRB was, and so we also have a pretty picture, just so we all we can make pretty pictures of anything. It turns out that having a pretty picture isn't actually part of White's mandate. But we have a pretty picture. The neutron star spirals in. It's accreting like crazy because it's cooling through neutrinos. It can accrete until it becomes a black hole. and then you now have this spun up star around a black hole, and you have a perfect condition for, at the time we were looking for models that produce nice disks around black holes to make gamma ray burst jets. So this is one of this class of black hole accretion disk, what we term bad GRB models. And we come up with this in the late 90s off of this. So here's the whole class of these black hole accretion disk models. It includes neutron star merge. This is a plot made by, funnily enough, the plot was made by Max Ruffert, but he based it on a talk that Stan Woosley wrote. But we all use Max Ruffert's plot because it's probably the clearest one we have, where you look at different ways to make accretion disks around compact objects. So neutron star mergers, black hole neutron star mergers, black hole white dwarf mergers. The classic collapsar model is just a fast rotating star that collapses and makes a black hole with an accretion disk. And then there's the helium. This is the helium merger model that we had proposed. So these were the kind of set of classes of models that we were studying. And the idea was for gamma ray bursts, you would make a jet, and you could make, depending on the model, we were arguing that the black hole white dwarf, helium merger, and collapsar would make long duration gamma ray bursts, and the neutron star and black hole neutron star mergers would make short bursts. I think the data is starting to, we were arguing this in the 90s. Now the data is getting more and more sure that this is a pretty reasonable picture. And so that things start to be filling out here. We have done simulations of these helium mergers. So we've taken a neutron star, let it spiral in all the way into its helium core, looked at the mass accretion, looked at the disk that it formed. Wei-Chen Zhang at Lawrence Berkeley National Lab did some calculations of this at the beginning of his thesis. We actually get nice disks. The problem is, and Di Matteo was the first to point this out, the angular momentum may be too high. When you spiral in, you spin up the star, and now I have this really diffuse disk. So the problem with this disk is now it takes a long time to accrete. And so it was longer than the 10 or 100 seconds of a lot of the long duration gamma ray bursts. So we had this problem where this model, where it became a little bit disfavored, is this model made disks that were too much angular momentum. And most of the other accretion disk models that we have, like the collapsar model, it's hard to get enough angular momentum. This one had too much. Yeah. Okay, so it was artificial viscosity from the SPH. You definitely get a different answer. This is not, this is not a done problem. And there's a lot of other groups working on it even more. But the viscosity is, we're using that artificial viscosity. We did a resolution study that would reduce that artificial viscosity. It didn't change the answer much, but it does change that inspiral time. And we, this is the whole thing with common envelope calculations right now is, do we trust our calculations? And people keep on, Ron Tam has like 25 papers on common envelope calculation. And it's because the numerics are hard. But I think at the level of getting that's an answer of how long does it take to inspiral. You're changing things you could change things by factors of 2, but you're not changing this basic. Yeah. So you could, and so where do you want to have the magnetic? So we do assume that once I spiral in and make this thing, I want to form a magnetic field in disk. I could be making magnetic fields in this, doing weird things with the magnetic. This is a whole, so I actually just hired a postdoc to work more on this topic. This is a huge topic. Enrico Ramirez Ruiz has been doing stuff with Mordecai McLeod. So there's people, this is not a done problem. It's just the basic physics, we know it's going to accrete like crazy. So we can change the accretion rate, but we're not going to turn it into a Thorne-Zytkow object. It's going to be something like this. And so we thought, but the problem was it had too much angular momentum. It didn't look like it was going to make normal gamma ray bursts. And then we had this Christmas burst go off, which had a couple features to it. Went on December 25th, 2010. It was a very long, so we got these very long gamma ray bursts. And now we have ultra long, that are like 10,000 seconds long. So we get longer and longer gamma ray bursts. But this was a very long gamma ray burst, so it was on the order of 1,000 seconds. It had a peculiar afterglow, especially in the X-ray, that had some blips in the X-ray that we were going, well, we don't know how to explain this. What's the model behind this? How are we going to explain these weird features? And one of the models that came out, there were several models, but one of the ones that came out was if you had a helium merger, during the merger process, you eject material. So you've ejected a large fraction of the hydrogen envelope, you've ejected some of the helium envelope, and I have this material out here. If I drive a jet, it's going to push through, but then it's going to actually, there's going to be shock interactions as the rest of the explosion hits this ejected material, and that can produce some extra features, some extra X-ray features as the shock goes through it. And if we actually knew the properties of these helium mergers, we could look at these properties and see, do we see them in gamma ray bursts? So we have done things where we said, we're looking at these mergers, we're looking at how far out the envelope might be. So this is the maximum shell radius versus the luminosity, where I'm basing the luminosity, assuming a simple Blanford-Znaic mechanism for the gamma ray burst. And so I have the maximum radius of this shell and the luminosity of the gamma ray burst. And we're looking for properties of gamma ray bursts to see if this helium merger can actually explain some of these properties. We're doing other calculations where we're actually looking at the jet interactions. And okay, imagine this is a jet. It's not, well, it's easy to imagine it if I don't actually, let's get back to it. I seem to be going, I have a 50-50 chance on which direction I'm going. So we're studying that jet and the interactions. That doesn't look like a jet. It's because we're doing a spherical explosion. But imagine that we're just studying the physics of that jet. We're looking at that turbulence that hitting that shell might do. We're seeing, can we explain properties of gamma ray bursts with these shell interactions? This is done by David Nielsen's group at Brigham Young University. So we're looking at that kind of interactions. So we're starting to say, can we explain these features of ultra long and very long gamma ray burst with this helium merger model? So that's one of the pieces of physics that we've been studying. The other piece of physics that we've been studying is, I showed you this plot of the entropy profile, and you see that it's convectively unstable. The entropy is going down as you move out. So the simple thing for those of you that don't study hydrodynamics, if you have something that's hot below something that's cold, it's going to want to boil. And this stuff, the conditions for these atmospheres are so dynamic that you can get very explosive outflows. And we've studied this for neutron star fallback in supernova. And if you have a little bit of angular momentum, you'll drive, I wouldn't call this a jet, but you'll drive bipolar outflows. And then this becomes something interesting as far as nuclear physics. And I wanted to spend my last little time discussing the nuclear physics from neutron star mergers, because I think we might be able to produce some interesting elements or isotopes during the neutron star common envelope environment. For these common envelope, for fallback, we get really dense flows. We can get to, they get dense enough that you can eject some neutron-rich material. The outflow is kind of strange because it does some bubbling around, so it can spend some time. And initially, we had proposed that this would make, could possibly make some R process elements through the ejecta. And this is one of the trajectories that we had in that outflow. And it produced very heavy R process elements. It did not, you can see it does not go that close to the neutron drip line. So it doesn't go, it kind of goes down and then comes back up. This was our initial idea of perhaps this was doing something different than full rapid neutron capture. So we had this new name for this new process. And then we talked to people who knew about R process and S process, and they said, yeah, we already named it. It's called I process, and then that led Falk to look for I process everywhere. But initially, we were looking in this fallback material. I'm not convinced that fallback can produce the R process or these kind of heavy R process elements in any large amount. And it certainly is going to depend on how you do the neutrinos and all of this physics. So it's as hard as doing anything with the supernova engine, but it is a different way of making getting some ejecta that might be neutron rich. So and just to show you, there's the dots are the signal we got from these fallback calculations, and the squares and triangles are the solar R process. So we're not making the right R process, but of course we didn't have the right nuclear physics in there either. So you could change this answer just by fixing the nuclear physics. But I think we have a lot more work to study that. What I want to look at is, what about if this was on fallback, but what happens if I had the lower accretion rates that we see in common envelope? What could happen there? And so we looked at some stars and said, what is roughly the accretion rates we expect onto the neutron star during a common envelope phase? And so you pick any one of these curves. This is enclosed mass, so the neutron star enters in the outside part of the enclosed mass and then spirals into the center of this of the star. We took a 20 solar mass star, a 15 solar mass star, and a 12 solar mass star at different times in their evolution, and asked what's the accretion rate with time, or with enclosed mass as it spirals in. And the accretion rate quickly goes up to a few thousand solar masses per year. And then when it hits the very center of the helium core, it starts to accrete at more like a million solar masses per year. So a tenth of a solar mass per second, which is on par with what we expect in neutrons in fallback conditions, where the accretion rate is really high. But there's a whole period there where you're getting accretion rates that are 10 to the 4 solar masses per year, 10 to the 5 solar masses per year, 10 to the 3 solar masses per year. Yes, sir. So it's accretion, but if you saw with the fallback, we actually got outflows because some of that material accretes in and then is driven out. So we look at the accretion rate, and then some fraction of that, and it's like 10%, gets re-ejected. So if you try to throw stuff onto a neutron star, it's very convectively unstable. It wants to eject that material. So we expect some of this material to come out, but it's going to be material that's gone all the way down to the protoneutron star surface and then get ejected. So we looked at these. These are models, actually, Sam Jones. Oh, sorry, I'm back. Get back up to my. Sam Jones had run some MESA stars. We looked at those MESA stars, and James Keegan said, I'm gonna look at. I have a profile where the material comes down in and it flows back out. I'm gonna ask the question of what kind of yields do I get? What kind of material will I get if I play with the accretion rate and say my neutron star spiraling, it's ejecting some of its mass. What kind of isotopes do I make? So a typical, here's just one example of some of the rate equations that were producing the yields. So they're color coded. The arrows are directing what are the directions that the isotopes are going as far as burning. So you can see you have you have a whole range of N gamma, alpha capture. You have all that physics going on. The magnitude of it is in color. So you can see kind of and the thickness of the line. So you can see kind of what isotopes are involved in this particular burning neutron star merger ejecta. The one thing that I should caution on is I only show one of these. We had some that went more neutron rich, some that went more proton rich in these ejecta, depending on the exact trajectories that we're modeling. So we're right now, this is again in its infancy. We haven't done a lot of study. We just wanted to look, does this make any interesting isotopes? And the yields that James Keegan got, and then plugged into population models, synthesis models of Benoit Cote to see where, what kind of elements are made in these neutron star mergers. And there's this mass range between about 70 and 100 that we actually can make a sizable fraction of the elements in our models. So the common envelope can be a real player in making this kind of mid-level heavy element production. So it's not something we can just ignore. We need to study it in more detail. We're not beyond that in saying how important are these common envelope events, because I think it requires much more detailed models. The physics that Sean was saying needs to be added to study these accretion. The ejection processes need to be studied in more detail. And right now, this is just using kind of this basic understanding we have from the models that have been done, and then doing nucleosynthetic yields from them. So we know we will get ejection when we have these mergers happen. We know matter will accrete onto the neutron star. We don't really, no one's actually done a calculation where it includes all of these effects, even in the common envelope phase. So there's a lot of physics that needs to be studied. I think it's an exciting field. It's not, this just shows that it's not a negligible contribution to the heavy element production. And I think that's where I'm going to stop. I think so. The issue is Thorne-Zytkow objects as something that is in the center powering a star will not happen. Neutrinos will sap out all the energy. Be careful when you use White's mandate. And the last thing is, I think there are some interesting objects, both gamma ray bursts and as nucleosynthetic yield sources that these mergers will have. And I think there's a lot of work to be done in this field, and it's very exciting. I'll stop there. So we used population synthesis models from Chris Bolchinski, and then so this tells you how bad this is. We take the population synthesis models. I have an analytic model for the inspiral time based on models that we've done for common envelope, which we all know are hard to do, so it's difficult. So I put in, that gives me an estimate of the accretion rate versus time, which then gives me an estimate for the ejection rate. I take the yields from a very simple model for how does the material go into the neutron star and get ejected, and then I'm plugging that back in through all of Chris Bolchinski's models and getting an average yield. So, and then Benoit puts that into his galactic. The neutron star, the population synthesis models from Chris Bolchinski are calibrated by the number of neutron star mergers he sees, the number of X-ray binaries. So he does try to calibrate his population synthesis models based on the observations of all the binaries that we see in the universe. And what I probably don't have, I think we only considered, this only has the errors from the doing the actual accretion process. So the green and the red are the errors just by not knowing how accretion on the neutron star is. We did study a few different models from Chris Bolchinski's suite of models to try to get an error on there. Those are also, they're big like these. So unfortunately, the error is about an order of magnitude, both from the population synthesis, and then another error based on not understanding the accretion process that is at least an order of magnitude. So you're looking at least a couple orders of magnitude error in what the rate is. This study was just to say it could be interesting. It's not to say that we know how much it's going to contribute. But so we're using the best we can right now with population synthesis models and what we know about accretion onto neutron stars and mass ejection in neutron stars. We may be underestimating some of the effects because I did a very simple matter flows in and then gets ejected, and we actually assumed there was no neutronization as the matter came in and got ejected. If there were even a little, that would change the yields as well. So you need the entropy to be above about 50,000 Boltzmann constant per nuclei to avoid the neutrino cooling. So, I mean, that's the thing with Thorne-Zytkow objects is you need a very high entropy. And remember, a normal star is 50. So they did it. Thorne realized his error as soon as he did his first paper and had this guy, Garrett Beal, do some calculations where he said, let's make a star that will not have neutrino cooling. So if you look at his star's entropy, he had an entropy where this was 50,000. And he made it do this on top of the neutron star. And then he had the problem is no star has an entropy of 50,000. So he had to have this entropy drop and come down to an entropy of 10. Boltzmann constant per nuclei down on the outside are 50 to look like a normal giant star. So this is what their model was this, which also might have been cool, except that this is a really huge entropy gradient. And so if you take a 1D code and you just say, just let this mix, it did this, they could prevent it from mixing too much. But if you put this into a 2D model, this would just all blow out and you'd have a pretty strong gradient. Usually when we're doing supernova, we're looking at pretty mild gradients in an entropy-driven convection. This is, when you go from 50,000 down to 50, it's a huge entropy gradient. But that's how you would, the way you could make it try and work is you could make a 50,000 or higher entropy Boltzmann constant per nuclei portion down near the neutron star, such that the entropy is so high, it's so diffuse there that there's not much neutrino emission. But you somehow cannot allow there to be an atmosphere that's too dense on that neutron star surface, or neutrinos will dominate. Yeah, because so you could get, I mean, you could get 10 to the 9 grams per centimeter cubed. So yeah, so well, so this is the thing is, I was trying to come up with a best case scenario where I thought there would be a layer of material that's really in the dense part that isn't ejected, and the material is coming in and going like that. But yeah, this is where we need to do real calculation, because I don't know. I mean, it could be anything. But I tried to be modest because I didn't want to get some really weird, you know. So the trajectories we chose were not, you know, they were based a little bit on calculations, but there's not been any real accretion models that were done in detail on this neutron star surface, unless you went and tried to extract from a supernova model and tried to use it as the data. So the issue is we haven't done that in detail for a nice neutron star doing accretion. I mean, I've done some papers, but I don't trust my simulations beyond that.
The question is, 3 or 4 years ago, there was an observational paper published where they for I guess a more stable Thorne-Zytkow object.
Yeah, so they're looking at very specific isotopic yields and say, this can only be produced if you have this neutron star doing this kind of physics. And the issue is that was I mean, we're doing it already with things like iProcess. So you can produce weird isotopes if you study the convective layers in more detail. So the funny thing is the yields they were seeing, they were publishing the paper at the same time that Falk-Herwig was talking about different iProcess effects in his stars. And it turns out the same weird abundances he makes with the iProcess are the ones that they're observing in these stars. So you can explain, there's multiple ways to explain it. And one of them doesn't invoke entropies of 50,000 near the neutron star surface. So I'm going to go with the one that's just convective. Yeah. Yeah. So I think that's what it is. I think it's not you know, the problem is if your only signature is a weird isotopic abundance, that's hard to justify ignoring neutrino physics.
Rubidium, for example, didn't actually turn, you know, it turned out they had a lot of the small parameters seemed to be incorrect. So the abundance might not.
Oh, okay. Well, then that makes it even less exciting.
What would be the energy range of the
They're typically weaker. They're typically less energetic, which but I can't remember the exact numbers. But you're looking at, you know, when they talk about isotropic energies, effective isotropic energies of normal gamma ray bursts of 10 to the 53 ergs, it's more like 10 to the 52 ergs. So about an order of magnitude less energetic, less total energy. And then remember that's in beam, so you have to correct for that. But it's about an order of magnitude on average, less energetic than normal gamma ray bursts. And that, if we knew what we were really doing when we do jets from gamma ray bursts, that, you could maybe make some predictions. It is true that if you have a lower accretion rate, you might not be as efficient at driving a strong jet. So the idea always was with things like white dwarf black hole mergers and helium mergers is, if anything, they would be weaker than the normal collapsar, which has a much shorter but higher accretion rate. So shorter duration but higher accretion rate for the collapsar.
Any other questions?